So let me remind, last lecture we started to move to quark level, and we described how beta decay and pion decay look like at quark level. So we continue now with strange mesons decay. And as you remember, we discussed before decay of K plus into muon neutrino and mu plus. K meson, K plus, at quark level is the combination of U quark and strange antiquark. So strange quark has strangeness minus 1. This is antiquark, so K plus has strangeness plus 1. And it has also isospin. And remember, at quark level, we have 3 quarks. 2 quarks, U and D, bring isospin properties. And strange quark brings strangeness. So they kind of share the roles. So although we see hadrons which have different characteristics, at quark level there are some specific quarks responsible for certain quantum numbers. Now, how this system can be converted into muon neutrino and mu plus? So remember, we described this by current composed of neutrino and muon. This transition, similarly to what we had for pion decay, can proceed via annihilation of U quark and S antiquark and production of mu plus and neutrino. Now, let me consider another decay. We have decay of K plus into pi 0 mu mu and mu plus. This decay can be described differently, slightly different way. So we have again U quark and strange antiquark. And to have this transition, what we need to have some disappearance of strange quark, because final system has 0 strangeness, and therefore S antiquark should be transformed in this way to U antiquark, and the system of U and U bar form pi 0. And here we have usual leptonic pair, mu mu and mu plus. So we also discussed so-called V-type decays. When we have transition of K0 into pi plus, pi minus. This is one of the channels which has been used to observe K particles, K mesons. So for this decay, we write the following. K0 bar is combination of D quark and S, again, antiquark. So both have the charge 1/3, and this is minus 1/3. And to have this decay, again, we need to eliminate strangeness, right? Final state has no strangeness. And what we can use here, we can use the current of a U and D bar. So when U is emitted and D is absorbed, and then S is transformed to U bar. Okay? So, this current is responsible for beta decay, right? And now see these two, or we can write in different way, these two form pi minus, and these two form pi plus. So this is the way how K0 is transformed into pi plus and pi minus. Now what is interesting that in all these cases we have transformation of U quark to strange quark, or annihilation of U quark and the strange quark, or transition of S quark to U quark. Here we deal with S bar, but we can write the same type of the diagrams for K minus and K0 bar. So the current, which is responsible for all these transitions, is also important. You see, we have different decays. However, what we realize at quark level, that the same quark transition is responsible for all these transitions. So we introduce strange current at quark level, which is U gamma alpha. Alpha here is for index 1 minus gamma 5, and S. And also we have here conjugate current when S is produced and U is absorbed. Okay? So, for instance, this decay is described by the following Hamiltonian. At quark level, the Hamiltonian is given by GS, strange or fermion coupling, square root of 2, then strange current, conjugate, and here is muon current, plus we have also the similar decays with electron, plus Hermitian conjugate. By the way, I have forgotten to say, for this type of the decay, as in the case of pi decay, we have suppression for light masses, light lepton masses. So this decay is also proportional to the mass of charged lepton squared, for the same reason as for pi decay. However, K has decay. I have deleted unfortunately this, but let me just repeat it. K plus has this decay when strange antiquark is transformed to U antiquark, and here we have U. Okay? So, and here we have muon and muon neutrino, but also we may have electron and electron antineutrino. Here, since we have 3 particles in final state, so this is pi 0. So this is 3-body decay. The feature which we have for 2-body decays, when decay rate is proportional to the mass of lepton squared, for 3-body decay this doesn't exist, and therefore appearance of electron neutrinos and positron is comparable with what we have for muon neutrino and muon. So in these 3-body decays of K meson, we have appearance also electron neutrinos. And this actually creates the problem for experiments. If you want to have pure beam of muon neutrino, better to avoid production of K mesons, go to low energies when you do not produce K plus. And therefore you are not producing electron neutrino flux. So this is the source of background for experiments which are looking for instance, oscillations of muon neutrino to electron neutrino. So this is the Hamiltonian, which describes strange transitions. But also we have a part of the Hamiltonian when we have S alpha dagger multiplied by D. Remember this V type of the events when we have in final state 2 ponens. That is described by product of 2 currents, and both of them contain quarks. This is strange quark, and this is with D quark. So this part of the Hamiltonian is responsible for hadronic decays of K mesons with final state containing pions. So now let us do another very important step in developments. Now you will see how the quark mixing is introduced. And ask questions if you have questions for this part. So, questions for this part? Remember when we discussed K decays in terms of hadrons or hadronic currents, we introduced the hadronic current of the following type. It was cosine theta Habibo multiplied by current with D quark plus sine theta Habibo multiplied by, so that was, let me put here, this is the current which is for K, and this is the current for beta. Let me put it this way. So this is neutron to proton, and this is, say, K meson to nothing or K meson to pi. So we have introduced combination of currents, strange current and usual current, hadronic current, and in this way we kind of managed to write Hamiltonian in very compact way. So then this hadronic current interacts with elliptonic currents. The Hamiltonian, remember, was the GF square root of 2 with unique coupling, and then it was hadronic current multiplied, so once I put dagger here, let me put dagger everywhere here, multiplied by elliptonic current. And actually total elliptonic current contains 2 terms. One is with muon and muon neutrino, and another one is electron and electron neutrino. So remember, this GS turned out to be smaller than G Fermi, and we accounted this by introduction of this mixing angle sine theta. So instead of 2 different G couplings or fermionic couplings, we introduced unique coupling. However, by price of introduction of this mixing. Now going to quark level. And we just realized how transitions are described at quark level. We should introduce the following current. Mu gamma alpha 1 minus gamma phi. And here combination cosine theta capital d plus sine theta capital s squared. So you see, this contains transition when we go to quark level, transition of s quark to u, and this one is transition of d quark to u when we go to quark level. So we can combine these two currents in the following way. We can put out u quark, because in both cases u quark is present. And then the rest is cosine d and sine s. So this term is giving for us the first current, which is responsible for pi and decay or beta decay. And the second one with u and s is responsible for strange particle decays. So we can introduce the combination d theta of d and s quarks, and therefore the current can be written as u gamma alpha 1 minus gamma 5 d theta. And so d theta is the combination of d and s quarks which form the current, charge current, with u quark. So we are saying that d and s quarks are mixed in charge current formed with u quark. So you see, this is the way how the mixing of quarks emerged. Remember, we started from decays of strange particle and usual non-strange particles. Then we decided to combine the currents which are responsible to these decays. And that led to mixing of currents. Going to quark level, we realized that that corresponds to mixing of quarks. You see, this is how the mixing of quarks emerges. And mixing means that both d and s quarks, they couple with u quark. And they couple with u quark in this combination, which we call d theta. We already discussed that the current structure actually corresponds to, eventually, to doublet structure of the theory, so we can introduce the doublet, which contains u quark and d theta. So when we combine in this way, the meaning is that we deal with charge current, which can transform d theta quark to u quark or u quark to d theta. Now, important thing that d theta is the state which has definite weak interactions. So it is this combination which enters the same doublet or the same current with u quark, and we are saying it has definite weak interactions. However, d theta is combination of d and s quarks, and those are the quarks which have definite masses. So the situation is the following. We have d and s, which are states with definite mass. And we have state d theta, which is the state with definite weak interactions. So, two states are not coinciding. We also can introduce S theta, which is orthogonal combination. That's another question, what we will do eventually with S theta. So we can introduce orthogonal combination. Let me introduce it here. S theta, which is cosine theta cavivo S minus sine theta cavivo D. So which is orthogonal combination. You understand what does it mean? Orthogonal means that if you compute d theta, ds, so S theta, then you will get 0 if S and D are normalized to 1. Check please. So if this is 1, S and S is 1, and D and S is 0, then this combination is orthogonal to this one, which means that they satisfy this equality 0. Please check this thing. So, we introduced two sets of the states. States with definite masses and states with definite weak interaction. So, d theta interacts with U quark, S theta doesn't. S theta doesn't enter the current with U quark. And this is the essence of mixing. So, when states with definite masses do not coincide with states with definite interactions. And we will see later the consequences of this. So, do not coincide. And this is the essence of mixing. Questions? So if someone will ask you how this mixing appeared, why we introduced this mixing? Well, this is historic development. We show that's how we arrived at this point. Well, actually remember that lepton mixing was introduced even a little bit before lepton mixing. Makina, Kagawa, and Sakata have written the combinations of muon and electron neutrino as combinations of states with definite masses. Of course, they knew already about the mixing of currents. And actually, they constructed some model in which there are mixing of currents and then mixing of leptons. But we will see, going to quark level, make things much more symmetric and simple. Okay? Well, actually, I believe the right way to understand things is really to see historic perspective and how things develop. Then you understand better why we introduce things in this way and not another, why these notions or those quantum numbers appeared and not others. So next concept which I want to discuss is universality of big interactions. What we have realized so far is that all weak interactions described so far have the Hamiltonian of the form current times current. All currents have B minus A structure. After introduction of mixing, all currents have the same coupling. The same coupling chicken. So we can depict the overall picture in the following way. We introduce quark current with mixing, right? We introduce electron current, and we introduce muon current. So far we have discussed three currents. Now, the product of this and this current is responsible for beta decay, for pi decay, for mu and scattering, also for K decay, right? These are the processes which we have studied. Now, the product of these currents is responsible for muon decay and for mu to E scattering, which we haven't discussed, but this is an important process which we will discuss eventually. So the product of these two currents also is responsible for pi decay, and actually this gives dominant mode of pi decay. It's also responsible for K decay, and again mu scattering on nucleons. Apart from this, of course we can consider product of this current on itself. Let me put this in this way. And this, for instance, is responsible for K decay into 2 pi, which I have mentioned. Weak decays without appearance of charged leptons. Now, the product of this current on itself is responsible for mu E electron go to mu E electron decay. And the product of these two currents, well, that would correspond, for instance, for scattering of muon neutrinos on muons. But this is something which we are, of course, not observing, because the muon is unstable particle, and then you need to create a muon neutrino. In principle, this process, of course, exists, but it hasn't been observed experimentally. And let me write this relation, which we had already. G mu square, and this is what actually we are calling GF in most of the cases, and this is G responsible for beta decay square plus G responsible for K decay. So let me just remind. And there is a Cabibbo angle which enters here, which actually tells us that the processes with strange quark are suppressed by sine squared theta cabibo, right? So S quark entered this current with sine theta cabibo, and when we compute the amplitudes and probabilities eventually, we square this, and then we get this sine squared theta. And what we are saying, these processes, these decays are cabibo suppressed. So this is the essence of universality. Without this, we couldn't write and create the standard model. So this is in the basis of the standard model. Now we can write the Hamiltonian using this in very compact way. Since all these products exist, we can introduce unique weak current which is the sum of quark current plus electron current and plus muon current. And then the Hamiltonian can be written in very compact way. GF square root of 2, G of dagger, G of. And this Hamiltonian describes all the processes with non-strange quarks, weak interaction processes, and also with strange quarks. So we managed to write everything in a very compact way, introducing a universal current of this type. Questions? Well, I should say that we made kind of shortcut in approaching this. In fact, the story was something like 10, 12 years to come to this conclusion. And in general, so what has been done, people have written Hamiltonians of general form, GF square root of 2, and then introduced different terms like C, this is some coupling constant, then U, gamma, mu, D, E. I just write a few terms, gamma, mu E, plus CA, the same. So U, gamma, mu, gamma 5, D times, can delete this, right? E, gamma mu, gamma 5, mu, plus CS, and all these are just dimensionless couplings. U, D, E, mu E, plus CP, which is U, gamma 5, D, E, gamma 5, mu, plus CT tensor, where we put G mu nu and G mu nu inside. So, the idea was the following. Let us write the very general Hamiltonian with all possible Lorentz structures. So, things which we are writing here in between the fields, what we refer to Lorentz structures. Of course, we are describing, if we are describing beta decay, and this is just for beta decay, then we need to still have U quark field, D quark, electron, and electron neutrino. This we should introduce. However, in advance, the Lorentz structure is not fixed. And people have written a general Hamiltonian with all possible Lorentz structures, and then eliminated or restricted all the structures, and eventually arrived at the dominant, at least what they have found so far, is this one, with CV equals to CA minus. And effects of these structures haven't been observed, and people put upper bounds on these parameters, CS and CP. And as I told you, that it took almost 10, 12 years to conclude eventually that we have this very, very simple structure. Well, this is not the end of the story, because even nowadays, people are looking for possible deviations from V minus A structure. And this is how we are looking for some new physics. So if some new physics exists beyond the standard model, and the standard model embeds this structure, then you expect some contributions of this time. May expect, if you introduce some new scalar fields which mediate weak interactions, then you get this. Of course, even Higgs produces a structure like this, Higgs boson, which is in the standard model. However, it's very strongly suppressed. It's very strongly suppressed. From time to time, people observe some kind of anomalies, something which doesn't match the standard model. So this is typical development these days. And in some cases, theoreticians are introducing these additional interactions and additional terms to explain anomalies. So maybe some of you will work on this, some anomalies, and then forced to introduce some additional terms here. Now, concerning this very simple V minus A structure, there's a big issue. So we have kind of asymmetry, because we have this V minus A, and one can wonder, why not V plus A? So if this structure exists or not. This structure exists in so-called left-right symmetric models, which it seems very plausible that this exists. However, we do not observe right currents. So this V minus A we refer like a left currents. Left currents. So why we do not see right currents? First of all, maybe they do not exist nowhere. But if they exist, then one still can explain the fact that we do not see these currents in the present day experiments. This is because mediators of these right currents, between right currents, are very massive. And therefore, although these currents exist, their interactions are very strongly suppressed. So GR for right current is much, much smaller than G Fermi. And this is why we do not see effects of right currents. Questions? Okay, so let me continue. Now we move to discovery of charm work. First introduction and then discovery of particles which contain charm quark. So I mentioned already that one of the heuristic important principles of development of theory is analogy. one, and we will elaborate more and more on this, is symmetry. And finally, unification. So these principles are kind of driving force to development of the theory, and I will illustrate this in many respects. There are two motivations to introduce another quark, which is charged quark. Remember, so let me first write. So one is precisely quark-lepton symmetry. So this one, how it works. You see, this is kind of an aesthetic principle. You want to have still something more simple. Actually, when you introduce symmetry, that usually accompanied by a reducing number of parameters. Symmetry means that you have some kind of equality of something, right? Which means that instead of two different couplings, for instance, you have just a single coupling. Now, we already have spoken that structure has doublet. So the theory has doublet structure, where we have doublet of mu e and e. We have doublet nu mu and mu, and they form the charge currents. And then we have doublet of u and d theta, which is a combination of s and d quark. Now, we also introduce s theta, which is orthogonal combination of, again, s and d quarks, but orthogonal to that which enters the doublet with u. Now the question is, why it is so asymmetric? You know, it's ugly. You know, here you have nice two things, and here it's just, you know, one, and then something which has not even pair. You know, it's a merry quark combination. So simple idea. So why not to make something more symmetric? And the idea was, after Bjorken and Leschel, and they were saying, so why we have 4 leptons and only 3 quarks? Why this S is in so ugly, S theta in so ugly manner enters the theory? Maybe some other quark exists, which is analogy of U quark, and which forms the doublet with S theta. Simple, right? Now it's nicer, I think. Now it's nicer. We have leptons, we have quarks, and there is correspondence between leptons and quarks, right? And this S theta is not just alone, you know, it has a companion here. Okay? This is the first motivation. The second one is the problem with flavor changing neutron currents. This is nightmare, you know, forever, actually. Even now we are fighting with these flavor changing neutron currents. Once we start to introduce something new to the standard mode, usually we are facing this problem. So you need to understand this very well. Flavor changing neutron current. So let me write it. The problem is that these currents are very strongly suppressed. And usually if you are doing something, introduce something new, stuff in your theory, you get a lot of these flavor-changing neutral currents. And as I said, this is the second motivation to introduce charmed work. So, in electrodynamics, we have neutral currents, right? When electron emitting gamma is transformed to electron, or U quark, again emitting gamma, is transformed to U quark. There is no transformation of E electron to muon, and this is gauge symmetry, which actually doesn't allow us to do this. Now we have weak interactions, which apparently has no such a feature like gauge symmetry, which is unbroken, like in the case of electrodynamics. And so the question is, can the current which transforms D to S exist? So this is flavor-changing neutral current. Remember, we referred to SU3 as SU3 flavor group, and D, S, U quarks are quarks with different flavor. By the way, in the lepton sector, we have slightly different terminology, and I will say this later. So we refer to U, D, and S, and these are mass states, as states with flavor, with definite flavor. Now we have change of D and S, and in this way we change the flavor. Electric charges of D and S are -1/3. So here we have no change of the charge, electric charge. So this is why we are referring to this as a neutral current. Electromagnetic is also neutral current, so this is gamma, and this we don't know yet, we haven't introduced something. But anyway, that would be neutral current. If this neutral current exists, then one would expect, if this exists, decay of K0, which is the combination of S antiquark and D, that would lead to decay of K0 into mu plus and mu minus. If of course such a current also exists, mu plus and mu minus. Okay? So it will be decay K0 to mu plus and mu minus. And the point is, although this decay has been observed, it has very, very small branching ratio, probability of the decay. So branching ratio, which we refer as the ratio of decay rate of K meson into mu plus mu minus over total decay, this quantity is something like 6.8 plus minus 0.01. 10 to the minus 9. Very strongly suppressed. More than 8 orders of magnitude. Okay, so how to explain this? Well, you can say, let us not introduce this current in our theory. Suppose we write Lagrangian which doesn't contain this current. The problem appears that even if you do not introduce flavor-changing neutral currents in your Lagrangian, the process still will appear, even without this current, as the effect of high-order corrections. So let me explain this. By the way, if somebody knows this story, tell me. Who actually studied these flavor-changing neutral currents in the course of particle physics? Well, some of you have the courses of particle physics. I'm just asking because I want to kind of to calibrate how detailed should I be. So you meet this for the first time, right? Okay. So what I'm saying that even if you do not introduce fundamental interactions with charge with this flavor changing neutral currents, the process like this appear as a consequence of already introduced interactions, but at high order. So let me explain this. We may have the following process. Let me draw and then I will explain. Here we have D, here we have S bar. So this is our K0. This is U quark. This is mu mu. This is mu plus. And this is mu minus. So now let me explain what is shown here. Here is just 4 fermionic interaction which contains U quark, strange quark, mu plus, and mu mu. And this type of the interactions is observed. This is nothing but decay of K meson into muon and muon neutrino. That is our starting point. So we have the currents with muon and muon neutrino. We have the current with U and S. And this vertex is precisely what we use to explain, to describe K decay. Now let us look at this vertex. Here we have D going to U and mu mu and mu minus. This should also exist. So this is analogy of beta decay when we have this current D go to U and we have current when mu mu go to mu minus. Well, actually this is precisely this process which was used to discover muon neutrino through scattering of muon neutrinos and emission of muon. So this is mu mu and go to P and mu minus. This vertex, this 4 fermion interaction is responsible for this process, and this one is responsible for K go to mu and mu mu. So these interactions exist. What I did, I just connected. So U is emitted here and absorbed here. Mu mu is emitted here and absorbed here. Once I have these interactions, it's unavoidable, no way not to write this type of the diagram or this type of the transition. And this is nothing but K0 go to mu plus mu minus. Okay? So, which means that even not introducing flavor changing neutral currents, I get the flavor changing processes as the result of charge current interactions. But in one loop, you have charge current in one vertex, you have charge currents in another vertex, and they together give a neutral current effect. So flavor changing neutral current appears as kind of effective result of already known interactions. Okay? Questions? By the way, have you started in a QED course or a field theory course discussion of diagrams or something like that? Not yet? Well, eventually you will learn things, but again, ask me if something is not clear here. So how do we compute the amplitude of this process? The amplitude of this process is proportional to G Fermi, right? We have 2 4 fermion vertices, And therefore now the amplitude already is proportional to G Fermi, not probability. Probability will be even G Fermi to the fourth power. Multiplied by S theta and multiplied by cosine theta. So where this appears? Here we have transition of U quark to S quark, and this is proportional to S theta because this current enters with S theta sine Kabino. This transition enters with cosine theta Kabino. So I'm making the shortcut notations. Then, when you compute the diagrams of transitions of this type, you have loop. And you introduce momentum of particles which are moving in this loop. And eventually you need to make integration over the momentum. And this integration from 0 to infinity, right? So what is important is energy momentum conservation of external particles. But if Q enters this vertex and Q goes out, then nothing happens with these kinematic variables, and so you can very easily satisfy energy momentum conservation of external particles for any Q momentum which is moving inside the loop. And in this way we are doing integration. So integration is of 4 momentum, Q4, 2 pi to the 4th. And then we are going around this loop and putting all the factors which appear in this loop. And so what we get, gamma mu 1 minus gamma 5. This is from one vertex. Then we need to write propagator of U quark, which is Q U minus M U Q U squared minus M U squared. Have you studied propagators in the Giovanni course? Have you started to do this? Green functions, propagators? Not yet. Oh, green functions. This is the same. Okay, so that element corresponds to propagation of U quark. Then we again meet the vertex, and this is the second vertex. We write gamma mu 1 minus gamma 5. And then propagator of neutrino, which is Q mu over Q neutrino squared. Okay? So these are just elements which I meet when I turn around the circle. So this vertex, then propagator of U, then this vertex, and then propagator of nu mu. And these factors which appear here describe propagation of this virtual neutrino and U quark which are moving inside the loop. Now, this integral is divergent. And we can simplify it a little bit and write it as d4q. And then what happens is that, you see, this is the mass. And here we have 1 minus gamma 5, which is projection operator, if you want, right? So you study the property. So if you move gamma 5 here and so attach with this gamma 5, then this disappears because of gamma 5, 1 minus gamma 5 properties. And so what we will have Q over Q, and I will just, Q should be practically the same as Q neutrino squared multiplied by Q squared from U quark and from neutrino, right? So that gives me Q squared, and it cancels with one of this, and I will get the integral, which is d4q 1 over Q squared. And this can be written as integral d, but it's fourth power, this is squared, no need to write more. which means that this is quadratically divergent integral. It's quadratically divergent integral. So, when I do integration, say up to lambda or q, then the integral will be proportional to lambda squared. So I can actually cut this integral introducing upper bound of integration. So this integral diverges, has ultraviolet divergence, as they are saying. It's divergent when q go to infinity. Okay? So the integral, so the amplitude then is given by proportional to g Fermi square s theta cosine theta multiplied by lambda squared. Well, in the theory, and in normalizable theory, good theory, we are usually avoiding these infinities in some way. To make estimation, we can do the following. By the way, usually this cut or cutoff of integration in a good theory eventually is related to some existence of some new particles and new masses. So eventually, lambda is some mass of some particle x. In a good theory. By the way, in electroweak theory is usually MW boson, so the mediators of interactions. Now, so we are in 70s, and of course you can suppress the integral, taking as small as possible lambda. Then your amplitude will be small. Now, how small can be lambda? If you take, say, lambda 1 electron volt or 1 MeV, this is not possible because by that time already people checked and there is no new particles at the scale 1 MeV. So the smallest lambda should be at the level of maximal, which you do not see new particles. So at that time people checked that below 1 GeV they do not see new particles. And therefore, minimal scale, which we can take for lambda, is this 1 GeV. Otherwise, we would see the particles, which are responsible for this cutoff. You understand logic? And usually it works. So, if we take 1 GeV for this scale, then we will get something you can estimate, or unless also to write some other factors here, that suppression can be at most, say, 3-4 orders of magnitude. And you need to have 8 orders of magnitude suppression. Well, this is the problem. The problem is that even if you take the smallest allowed lambda, we will get eventually the amplitude and branching ratio, which is not 10 to the minus 8, but 10 to the minus 4, 10 to the minus 3. So many orders of magnitude above what is allowed. Ask questions. So I'm discussing this problem for this case, for specific K0 decay into mu plus and minus. But this type of the suppression you need and situation you will see in many other places. So it's a very generic problem. Why? This is why it is important to know this and to remember this. Now, what was solution of the problem? And solution of the problem was the following. So let me deal with this. The solution of the problem suggested by glacial Heliopolis and Miami. And as you know, Miami is the chair of our advisory committee of ICTP. So you can meet him actually sometime teach you that. So they suggested the way to avoid the problem, and after these names, this mechanism was called Jim mechanism. So what they suggested actually, what already appeared before. There is a force quark, and so the whole system is u d theta, charm, and s theta. So solution of this problem is when we introduce force quark, which is in the same doublet with this s theta combination, what we have discussed. So how this solves the problem? The point is that if you introduce the second doublet, then another diagram will show up. Let me see what I can delete. Okay, so let me delete this. So if you introduce the second doublet, then the diagram will appear with all the particles to be the same, but here, instead of u quark, will be this charm quark. This is one point, and what is crucial is that now, what is staying here, and here we have transition of d quark to charm, so we need to see parameters here in this combination, and this transition is proportional to minus s theta, and this is proportional to cosine theta. That's s, and this is d. So charm likes strangeness, and therefore this transition is not suppressed by Kabir binding. So remember what is this combination. S theta is cosine theta strange minus S theta d quark. So two important things. One is now Kabir suppressed is the current with d quark. And the minus sign here appears, which you need to have orthogonality of s theta and d theta. And so we have here minus s theta, cosine theta, and here is sine theta and cosine theta. And therefore, if the mass of charm quark equals the mass of u quark, you will have complete cancellation of these two diagrams. Clear? So they have completely the same structure, and the only difference is this sine and cosine which you are ascribing the vertices. The product is the same, this sine, cosine, here it will be cosine multiplied by minus sine. The same, but the sign, overall sign. And therefore these two diagrams have opposite sign, and if all the masses are the same, then they cancel. Now, charm quark or charm masses haven't been seen by that time, so for this you need to have charm quark to be heavy enough. And so clearly you have no equality of this type, and if you have no equality of this type, then you will get the following suppression. It will not be complete cancellation, but it will be strong suppression. So let me describe this. So essentially, I will focus on elements which are different in two diagrams. So in one diagram, you will have q squared minus mu squared, and another diagram q char minus m char squared. So I omitted all other elements because they are the same for the two diagrams, the same but propagator of quark, which is here and here. And that is described by this factor, which is given by then mc squared minus mu squared. And here is q squared minus mu squared multiplied by q squared minus m char squared. So, this factor, if I neglect masses in denominator and I make integration over q from 0 to infinity, and so the most contribution comes from big Q, then this will be given by delta m squared over q to the fourth power. Okay? So now the integral over q becomes logarithmically divergent, not linear, not quadratically. So we have d for q squared over q6. So we have additional power of q. And we have delta m squared here. And again, if we do cut off, then that will give for us it will give for us logarithmic. This is logarithmic divergence. It will give delta m squared and logarithm of lambda squared. Collecting all the factors together, we obtain the following expression for, let me write already, rate of the decay. Gamma mu mu. That will be proportional to sine theta squared multiplied by cosine theta squared. So the amplitude is proportional to sine times cosine, and we compute probability, so we square this. And then additional factor appears, which is proportional to delta m squared over lambda square, and this is square. Even for 1 GeV, you already have very strong additional suppression. But really, you can explain the smallness if lambda is proportional to something like the mass of W boson, or around 100 GeV. Now lambda is in denominator. So, if lambda, and at that time it was known, if lambda is of the order of 100 GeVs, you will get enough suppression. So the suppression comes from sine theta squared, which is not so big, but mostly from this, because here the difference of masses, say 1 GeV squared, U quark is very light, over lambda, or let me write this, 1 GeV over 100 GeV, and everything should be in the fourth power, right? So here square and here squared, fourth power. You have here 10 to the minus 2, and here is the fourth power, you will get immediately 10 to the minus 8 suppression, right? So we have also some other factors, and you have here suppression, and so eventually you can explain the absorbed branching ratio. So it is this factor which is called Jim factor, which is proportional to delta m squared mass difference squared, and delta m squared probably I should write this, but delta m squared is mass of the charm quark minus mass of U quark squared. So this is very small, and therefore this is mass of the charm squared. There were papers, actually, in which people made the first estimation what should be the mass of charm quark to explain sufficient suppression of flavor changing hint of kinds. Questions? And of course, in the limit of equal masses, we will get 0. We will have complete cancellation. Everything clear?
I have one question. In the amplitude, should we consider Diploma and quark vertex? Just we consider interaction of the quark Diploma and
the vertex.
should we consider each of the vertices of the quark and Diploma?
Without lepton? I'm not sure that I understand. So we have these processes when we have S bar U mu and nu mu. We have this vertex, and we have vertex of U, D, and nu mu and mu. So this is what exists. Now we want to write something which actually can produce for us transition of K0 or S bar D into mu plus and mu minus. I don't think that you can use some other vertices. So we cook our diagram from these interactions which exist, which have been proven, measured, that exist. Using these two interactions, we can produce the diagram which gives K0 to mu plus mu minus transition. Now say again which currency you want to use in additional. So this is our usual currency, right? So this is what we studied with.
Yes, there is the one interaction point, but there is the four different vertices.
No, two vertices.
Yes, two. But I am just confused about what about other two vertices.
Which are?
I think U and D. U and D have also vertices or some propagator.
So something like this when you have U, D, U and D. Yes, such a vertex exists with this current, so you can write.
Yes, I am.
You can write this U, S, and here U, D, for instance. This exists, but it is not relevant for this process because you need to produce muons. You need to have still lepton pairs in your vertices. And this is why we are using these two. Maybe I don't understand quite well your question. Can you say again, and maybe in some other way?
In the amplitude, we just write the interaction point, but there is some B quark and S quark and muon plus and minus. There is also some propagation vertices.
No, we are not saying propagation vertices. So we are saying that we have these two vertices of interaction. Now, What we are doing, we are connecting this U with this U. And we are connecting this nu and with this nu, because these are the same particles. So we are describing what propagates is nu mu from one vertex to another, and U, which propagates from one vertex to another. And other particles are just external to this. These are free particles which are in initial state and a final state. So again, what happens is that you have two space-time points of interactions, x and y. What happens is that, say, S antiquark and muon appear from this vertex, and d quark and another muon appear from this vertex, and you have something which actually communicate between these two vertices. You need to have some mediator, and what plays the role of mediator is this u quark and nu mu. So that's what mediates the interactions between these two vertices.
Okay, thank you.
More questions?
I have one question. Does the introduction of this new quark does not affect in any sense the fundamental SU3 symmetry?
Sure, absolutely. Now we will move from SU3 to SU4. Since we have another quark, another flavor, we are forced to move to extend further SU3. To include this fourth quark, now this flavor symmetry will be SU4. I will discuss this a bit later. More questions? Okay, so before discussing experiments in which particles containing charmed quark have been discovered, I need to introduce some kinematics, which is actually very important for many other discoveries. I think this is what you need to know. This is kind of minimal thing you need to know about kinematics at least. So I'll start, probably finish next lecture. So you'll have 10 minutes. Which are crucial for discoveries of particles. You will have exercises, and you will see that all further discoveries, including Higgs, W bosons, they are based on these kinematics. So this is why it is important to know. One notion we have already introduced, and this is total energy in the center of mass. In the center of mass system. So now I a bit generalize this notion and then apply for some specific situations. Suppose we have some particles in initial state which collide, and then we have some particles in the final state. So we have particles A1, A2, AN in general, which are transformed into some final state. So the process is like A1 plus A2 plus go to some final state. Actually, mostly we will use just two particles in the initial state. Now, let us introduce four momenta of these particles, P1, P2, Pn. And then total energy in the centrum of mass squared is introduced as the sum of 4 momenta of all the particles in the initial state, which can be written as the sum of energies squared minus sum of momenta squared. This is Lorentz invariant. You can compute it in any reference frame. And total energy in the centrum of mass is square root of S. Now, the system, a centrum of mass system, is defined as a system in which the sum over momenta is 0. So you always can find the system when the sum is 0. And then square root of S in this system will be square root of sum of the energies squared, and this will be nothing but sum over energies of particles in this system. So this is the origin of this name. This is really the sum of the masses over all the particles, right, in this system. Although it's invariant, Lorentz invariant, but it has physical meaning in this system of coordinates, and which is defined in this way, so that square root of S is given by the sum of energies of the particles. Let us consider some specific situation. When initial particles are transformed into single particle. So to say, we have the process A1 plus AN, and that is transformed into a single particle X. So we have a diagram of a process like this. Several particles, 2 and more particles in initial state, and a single particle in final state. One example, important, is annihilation of the plus and minus. I mean, this is the simplest example into some particles. So let us write energy and momentum conservation for this reaction. The sum over momenta in initial state equals momenta of the single particle. And we can write for energies that the energies are equal to the energies of X. Now, what happens in the centrum of mass system? In centrum of mass system, this sum, by definition, is 0. And therefore, Px is 0. So which means in this frame, this particle is produced at rest. And therefore, its energy just equal to the mass of this particle. Now we can write what is square root of S. And square root of S in this system is the sum over particles. And thus from this equation, we get that this is the mass of the particle S, that square root of S equals the mass of particle X in this system. Agree? Or not agree? So this is energy momentum conservation. We go to centrum of mass system. This is 0. And therefore the particle is at rest. and therefore Ex is just the mass of this particle. And therefore this, and this system, square root of S, and this is Mx, and therefore we get that the square root of S equals the mass of the particle. So very important conclusion then. If system of particles transforms or annihilates in a single particle into a single particle X, then total energy in the centrum of mass of this system gives you the mass of this particle. So you measure this, you know what is this, you collide particles, and then you observe, if you observe that only single particle is produced at a given square root of S, then this square root of S gives you the mass of the particle. So this is actually how we define or measure the masses of new particles produced in collisions. So square root of S is Lorentz invariant, and therefore you can use any reference frame. We can use laboratory frame. So usually we are using laboratory frame. We collide particles. In final state we have some moving particle also, but we compute square root of S, and it gives us the mass of this produced particle immediately. But surprisingly, that's why I'm doing this kind of in details. Sometimes, students have a problem with this. But I would suggest just to repeat again all these computations. Now, suppose we have, as usual in an experiment, we can change square root of it. So we change the energy of colliding particles. Then if square root of S is smaller than Mx, then we are not producing this particle. We cannot produce. We have not enough energy. Particle is not produced. Now, if square root of S equals Mx, then at this square root of S, we are producing this single particle and nothing more. Now, if square root of S is bigger than Mx, then of course we have enough energy to produce particle X. However, we have even some additional energy, and therefore we cannot satisfy energy momentum conservation if only a single particle is in the final state. However, if some additional particles are emitted, plus additional particles, so in final state we have A1 plus AN go to X plus something else, say Y. Photon or something like this, then we can satisfy energy momentum conservation. From this picture, we have the following. We change the energy of square root of S, and then at some point, particle X is produced. When we continue to increase energy, then some more particles are produced. However, the initial energy, square root of S, at which particle appears, gives us the mass of the particle. So I'll stop at this point. Please ask questions. You will see realization of this picture in a number of discoveries. remember this, we already have mentioned this before, so if you want to discover some new heavy particle, you need to have enough energy. And the correct measure of availability of energy is square root of S. Square root of S, this invariant is the measure of what you can do with your accelerator. So if you collide, say, some particle which has mass, has energy E with some particle at rest, then available energy, you need to compute it. You need to compute square root of S. This is what you then can use to produce some new particles. Questions? And we will have some problems, and I will prepare next set of the problems to the next lecture. I expect that on Thursday you will give me solutions. I will try to check solutions tomorrow, so I had no time to do this, and nobody is helping me. So before again, postdocs and postdocs. Let me switch over.